Good afternoon, everyone, and welcome to the Georgia Smart webinar series. I'm Greg McCormick, Director of the Georgia Smart Communities Challenge. Today's webinar is the third in our series, and we're going to be hearing from Georgia Tech research partner, Angshuman Guin. We're excited that he's here with us today. He's a senior research engineer in the Civil and Environmental Engineering Department at Georgia Tech. Dr. Guin has been at Georgia Tech since the late 1990s, where he earned his master's and PhD in Civil and Environmental Engineering. He's a transportation engineer with significant experience researching intelligent transportation systems, traffic safety, traffic simulations, and his recent work on freeway operations, ramp metering, and connected vehicle technologies. He's worked on several state and national level initiatives, including projects from the National Science Foundation, U.S. Department of Transportation, Georgia Department of Transportation, and GRTA. So thank you so much for being with us today, Dr. Guin. Before he begins his presentation, we have a few housekeeping activities. This will be approximately a 1-hour presentation, 1-hour webinar with a 45-minute presentation and about 15 minutes for Q&A afterwards. Please make sure that your microphone and your video is muted so that we limit interruptions. You can submit questions to the chat area. Feel free to submit those throughout the presentation, and they will be answered after the completion of the presentation. So thank you so much, everyone, for joining us in our third of the series of the Georgia Smart webinar as part of the Georgia Smart Communities Challenge. And thank you, Dr. Guin. Welcome.
Thank you, Greg. All right. Good afternoon, everybody. Let me just jump straight into this. And if it responds. Okay. So let's start by taking a moment to look at this chart here. This chart shows the number of fatalities from roadway crashes in the United States by year since 1975. While we see a slow trend in the reduction in fatalities over these years, we still have at least 35,000 deaths per year due to traffic incidents. A significant part of these are related to drunken driving, drugs, and drowsiness. These are very much preventable. No wonder when the concept for connected vehicle promised the possibility of prevention of crashes, it was welcomed with wide open arms. The challenge, of course, has been the implementation. We have seen the concept go through multiple reincarnations over the years. It has been called different names over different periods and in different parts of the world. Vehicle Infrastructure Integration, or VII, Vehicular Ad Hoc Network, or VANET, are some of the popular ones. Over the last few years, there have been a steady stream of projections that we will see the market flooded with connected vehicles in the next 3 to 5 years. While that has not come to pass yet, and a lot of that has to do with legislative policies or lack thereof, things are fast taking better shape in terms of the maturity of the technology on all fronts. Connection from vehicle to infrastructure to V2I, V2C vehicle to cloud, vehicle to pedestrians, V2P, other vehicles, V2V, and ultimately vehicle to X, that's vehicle to anything. Well, to complicate things further, the Betamax versus VHS style battle still rages on for the backbone networking network regarding whether the implementation of connected vehicles will use dedicated short range communications, or DSRC, or cellular microcell-based network or 5G capable equipment. The US DoD push has been for DSRC, while cellular network service providers have pushed, obviously, for 5G. In spite of their interest in staying neutral or agnostic to the underlying technology, automobile manufacturers have been forced to make a choice to start their integration with one technology or another. Since we have Volkswagen, Ford, Audi, BMW, etc. on the CV2X, or the 5G and 4G bandwagon, whereas we have had manufacturers like Honda, Toyota, and Nissan who have sided with the DSRC implementation, and they have started integrating equipment capable of DSRC into their vehicles. So the state of Georgia has recently moved to the forefront of connected vehicle research and development, as well as field deployment. The first of the DSRC road unit deployment started with the North Avenue Smart Corridor project that developed as a result of collaboration and partnership between Georgia Tech and the city of Atlanta. DSRC equipment was deployed at 22 intersections on this corridor. Since then, GDOT has deployed DSRC equipment at 54 more intersections on State Route 141 and on Ponce de Leon Avenue. More recently, Georgia Smart kickstarted the Georgia Smart Communities Challenge. And one of the first 4 winners of this challenge was a project led by Gwinnett County, where Gwinnett County is developing a connected vehicle technology master plan. With 725 traffic signals in the Gwinnett system and 185 RAM meters in and around Atlanta, and the 1,700 signals on the GDOT's regional traffic operations corridors available for deployment of this technology, the impacts of these initial projects can be tremendous. In the rest of the presentation, I'll discuss the connected vehicle research aspects of these 2 projects and the progress we have made so far. The North Avenue Smart Corridor project was conceived as a public demonstration and living lab for the Internet of Things, or IoT deployment, for data collection analytics, autonomous vehicles, and partnerships. If you can think of a smart city technology, you will likely find it there on this corridor. The corridor has connected vehicle infrastructure deployed, of course, but there are different vehicle detection cameras for each camera at each intersection. There are bike and pedestrian detection sensors. There are smart waste and recycle bins on the sidewalks. There are weather sensors deployed on the street light poles. The intersection signal controllers also feed into the Travel Safely app, which shows a countdown clock for the status of the traffic signals in real time. There have been demonstrations of automated vehicles in the Ponce City Market parking lot, and there are currently plans to deploy automated shuttles on the corridor. The connected vehicle equipment. So the connected vehicle equipment essentially consists of a roadside unit, or the RSU, and that can broadcast messages such as the signal phase and timing information out to vehicles, as well as receive the messages broadcasted by the vehicles. So to communicate with the RSU, the vehicles need to have an onboard unit here. The picture you see in the middle here. So the OBU transmits out the vehicle's location, and it has a GPS antenna. It has the white antennas you see there are the Wi-Fi antennas, and there's a couple of DSRC antennas. So the OBU transmits out the vehicle's location and receives messages broadcasted by the other OBUs or the RSUs. The OBUs can connect to a visual interface that can be seen by the driver, or the information can plug directly into the vehicle's CAN bus if that integration is desired. So eventually, the driver can be taken out of the loop, and if there is an emergency braking is required, the vehicle can automatically brake. It's with the advent of the autonomous vehicle, or if depends on how far we go with the integration. Right. So the first 2 screenshots here show the signal status at an intersection. So you have a countdown clock which shows how many seconds you have till you get a green at the signal. And the third screenshot here shows a blind spot warning where an OBU is detected in close proximity of the vehicle. In this case, it was just 2 OBUs sitting right next to each other. No, I did not have another vehicle with an OBU in my blind spot. All right, so what is Georgia Tech doing here? Georgia Tech is developing a hybrid simulation model for this corridor. The hybrid essentially implies that the simulation runs in a data-driven mode by ingesting real-time information from signal controllers and vehicle detection equipment in the corridor under normal circumstances, but can fall back on running based on pre-programmed information in case there is failure to receive updated information for the field due to any reason. And the reasons can range from equipment failure and communication failure to lack of development of equipment or lack of deployment of equipment at the intersection. Is that this model lets you simulate corridors that have partial deployment or connectivity as well. So how does this work? This uses in-field detectors and signal control status data and connected vehicle data to drive the signals and vehicle demand in the model. It generates travel time, energy, and emissions KPIs for the corridor in real time. So the purpose of this model is to help assess feasibility of using a real-time data-driven transportation simulation model to provide dynamic operational feedback in a real-world environment. The overarching goal is to improve the quality of life at cities, of the city stakeholders, the residents, the people who work here, as well as the visitors. So this dovetails into the smart city vision of integrating smart technologies with the physical infrastructure by providing real-time data integration into operational analysis. The modeling architecture leverages big data concepts in the ingestion and extraction transformation load, or the ETL process of the data into the simulation. The final vision here is the dynamic data-driven application systems approach, where the current state of the system is used to estimate the potential future state with no interjections. The required performance metrics are estimated for the future state, and the required adjustments are then made are computed to optimize the performance. These adjustments are fed back into the system in real time to be implemented by the vehicles or the traffic signals, and that affects the future state. The project here under progress, it does the first two steps. The third step and the closure of the loop is currently beyond the scope and resources of the project. Okay, so the first two steps involves the computation of KPIs. And while some KPIs such as the KPIs are key performance indices, while some of these performance indices such as travel time can be directly measured in the field or computed based on spot measurements in the field, the energy and emissions KPIs require much more detailed data. Such detailed data is expected to come from the basic safety messages. Let me go back to the previous slide. From the basic safety messages generated every 10th of a second by the connected vehicles. However, in our current deployment state, while we have a meaningful number of RSUs deployed, there are not too many connected vehicles in the field available to provide the BSMs. To overcome this problem, we use synthetic BSMs generated by the simulation model. However, to keep the synthetic BSMs realistic, we use real-time data from the field to drive the model. So our initial model consisted of 17 intersections on the North Avenue corridor, where we had both the vehicle counts and signal timings. Excuse me. The first model worked purely on pre-programmed signal times and typical input volumes. Then the next step was to adjust the input volumes with real-time volumes and replace the signal timing with real-time status of the signals from the field controllers. We started off with replacing data at two of the intersections, the Glen Iris and the Pond City Market intersection here. And then currently we have it across the system. So we have all the signals feeding off of real-time status and volumes. So for the simulation, we use the VISIM microsimulation package. VISIM allows us to model individual vehicle behavior, the traffic control devices, the intersection and interchange geometries, the dynamic demands, the merging behavior, vehicle routing, etc. Essentially, it's a microscopic simulation model. The basic model architecture has three primary components: the data ingestion module, the simulation module, and the KPI generation module. So each module dynamically feeds into the next module. Each process essentially needs to be able to run faster than real time so as to keep up with the second by second real time data updates. The data ingestion module essentially feeds the vehicle count data and the signal status updates to VISIM. VISIM simulates the movement of the vehicles in the network. From the trajectory outputs of the vehicles in the network, the synthetic BSMs are generated. The EPA moves model is then used to process these BSMs on the fly to generate the energy and emission KPIs, which are then pushed out to the visualization. Let's look under the hood of this architecture. Things get slightly more complicated. The success of this approach is heavily reliant on the real-time nature of the data availability, as well as execution of the simulation and the KPI, the key performance indices computation steps. We had to develop a message handling framework, which makes the transfer of data transparent in the underlying process. With the use of sockets, ASN1 encoding and decoding of BSMs and the SPAT messages, the sanitization of the input data, managing the synchronization across applications, etc., are all made transparent to the simulation by the message handling framework, which is built on top of this Python-based um, web service that provides a REST application programming interface to the rest of the modules. So let's take a closer look at component 3, the dynamic KPI generation component. So VISIM generates the trajectories of the simulated vehicles and writes it off to the trajectory file. The trajectory file is skimmed continuously for new trajectory information to generate the synthetic BSMs. The BSMs are processed to extract the acceleration, speed, and vehicle type information, which is then used to plug into EPA's moves metrics or moves model to generate the energy and emissions KPIs. Now, the computation of the KPIs in real time is made feasible by leveraging Georgia Tech's moves metrics approach, where a huge multidimensional metrics of emission rates have been generated by pre-running the moves model for a wide array of variables. Since essentially the BSM is boiled down to a VSP bin that is used in conjunction with the appropriate energy and emissions profile that is obtained from a lookup table from the moves metrics to generate the energy and emissions values. The energy and emissions values are then fed into the visualization module. So we have one of these KPI visualizations online. So I have captured a video a few minutes back here that we can play back here. So what we have here is while we are generating the real-time update interface, we have created an offline real-time version. This version is a playback of the results from Monday, January 14th, which you see here in the top right-hand corner in the label, but the time is synchronized to the current time. So I was capturing this around 11:47 a.m. in the morning. So that's the time it's showing up. So this page shows the CO2 emissions on the roadway segments that are each 200 feet long. To reduce the noise in the data, we use 20-second moving average, and that is recomputed and updated every 5 seconds. So if you look at this, once you'll see the segments updating every 5 seconds, the colors are changing. So if you zoom in and track the movements at a particular signal, you can easily see the hard accelerations associated with the vehicles leaving the stop bar. You can essentially see the waves of high emission flowing through the system. So while this is interesting and Since I can look at this all day long, let's keep moving. So we have tested the model to check for the model sensitivity to real-time inputs. Since the pre-programmed inputs are fairly realistic, we did not expect a large difference between the results from the preset inputs and the real-time inputs in this case. So the energy versus time plots pretty much confirm our hypothesis here. Once you see, as there is a difference between the blue line here with the preset inputs and the red line, which is the real time input. So so there is somewhat of a difference, but it's not a huge difference. So we can see that the model is responding to the real-time inputs. At the same time, it's not widely deviating or giving us inordinate results. So we also looked for stochastic variability by changing the random seeds in the model. The plot of the travel times versus simulation period here shows that the variation here again is within plausible bounds. There is variation. There is a difference from the real-time inputs, which are in purple, and the preset inputs, which are the pre-programmed inputs of the signal times and the volumes, and that's in green. So you see a difference here, but again, means it's within plausible bounds. So to summarize, we have seen that it is plausible to build essentially a digital twin, a data-driven simulator that reflects the current field conditions. Essentially a digital twin of the corridor. So the challenges we have faced in making this work has primarily been in the integration of the real-time data into the simulation model. Is things that we take for granted in a regular simulation model becomes significant challenges when you're trying to drive the model with real-time data, and ensuring the timely arrival of data over the cloud, and how much data and at what aggregation level do you pull over a slow network such as a cellular network. How do you minimize the data transfers? How do you deal with missing data? And how to validate the data accuracy on the fly? Also, how do you manage the storage of high volume inputs and even larger high volume output streams? These are all interesting research questions in themselves, and we have answered some of them. Some questions remain unanswered, and we are still looking for better, more efficient solutions for those. So anyways, where do we go from here? One of the obvious impediments for any kind of microsimulation is the scalability. And due to the serialized nature of the simulation model computations, there is a limitation on how big a network you can run faster than real time. Typically, in these microsimulation models, they do not scale very well across the computation cores, since they typically run as fast as a single core of the machine can run. So we very soon reach a limit of the number of vehicles that can be processed in real time by the simulation model. So the way to get around this is use distributed simulation solution. But then again, when you are using a distributed simulation, how do you match up the vehicles from going from one simulation piece into the next simulation, the adjacent simulation piece? Those are things that are active fields of research. So The other thing that we are trying to do here is we are planning out a validation experiment. So, and now, although we have a good RSU infrastructure built, the number of OBUs in the field is very limited. Most of the time, the only OBU that I see is my own or someone going out there to do some maintenance. So due to the lack of OBUs, the sample size is of the BSM data that is streaming in is very small. So we intend to do a field experiment with a fleet of 10 vehicles equipped with OBUs traversing the corridor simultaneously. So we get a steady stream of BSMs from the corridor at the same time. This will let us do comparison of the KPIs that we can generate from the field BSMs versus and compare it with the KPIs that we can generate from the synthetic BSMs with different levels of penetration. So we can take all the vehicles, that is 100% penetration of OBUs or connected vehicles, and then we can reduce it to multiple levels, 90%, 80%, 10%, whatever. So we can study the effect of the different levels of penetration of connected vehicles on the corridor, and we can compare it with the real world BSMs to make sure we are we are close to reality. Anyway, so we are also looking at how to get the next phase of creating the feedback loop. So we can fast forward the simulation currently, as long as we can run faster than real time. But the challenge is, once we have seen the future, we have fast forwarded and seen the future, how do we come back to the current state and run the simulation again by tweaking the parameters and get to the future we want? And so saving the current state and restarting the simulation from a saved state is non-trivial. So that's something we need to figure out. And eventually, what we are doing in the simulation that goes into the field, once we build the capability of the vehicles actively being able to implement what is being pushed out to them, then this whole feedback loop gets completed. Anyway, I will leave you with that thought while we move on to our other connected vehicles project. So in 2018, Georgia Tech, in partnership with several public and private sector public and private sector members, started the Georgia Smart Communities Challenge initiative. You can find out more about this initiative from Deborah or Greg, but essentially, out of 20 proposals, 4 initiatives were chosen that leverage the smart cities ecosystem approach. Each community partnered with a Georgia Tech researcher for their project. I am the research partner for the Guin Connected Vehicle Technology Master Plan project. Given that the uncertainties and the rapid evolution of technology in front of connected vehicles, this project's objective is to set the standards for the application of connected vehicle technology with the goal of improving safety and mobility. The standards developed herein are expected to have broad applicability across the region in terms of aligning the visions, expectations, and technological approach towards deployment and application of connected vehicle technology. A wide range of stakeholders, including fire, police, the community improvement districts, the cities, neighboring countries, and GDOT have been involved in this process. So, for initial planning purposes, instead of targeting instead of trying to address the entire county, the project focuses on the Peachtree Industrial Boulevard corridor. This corridor has infrastructure maintained by the county. It has a good mix of activity centers as well as rural sections. It passes through 7 different cities, which makes it appropriate target for stakeholder enrollment. Also, it is amenable to development and testing of applications that are targeted at improving safety and mobility, with 6 fire stations in close proximity of the corridor. And the corridor is also a target for the transit system expansion. As a traffic operations engineer, I see every intersection as a bottleneck, and as a safety engineer, I see every intersection as a zone with multiple conflicting vehicles and people movement that leads to crashes. From that perspective, intersections present opportunities for improvement all the time. As you can see, this corridor has ample opportunities for CV equipment deployment. The question is, how do we leverage the deployment to improve safety and mobility? So the Gwinnett County team has identified several potential applications that can take advantage of the connected vehicle technology. Some of the top contenders in the space are the emergency vehicle preemption and signal priority for transit and freight, where the particular class of vehicle is given preferential treatment in navigating through intersections. The concept of signal preemption and priority is not new. It has been here for a while. However, connected vehicles present an unique opportunity to make this seamless and automatic by taking away the need for operators of the emergency vehicles or the transit or freight vehicles to actively take action, such as pushing a button to ask for a preemption or a priority. Similarly, by automating the detection of pedestrians and other vulnerable road users, possibly through applications on their phones, or getting them to push a button or swipe a card at the signal. The process of giving priority to vulnerable road users, or giving them the extra few seconds to the pedestrian who needs to move slowly, is made seamless by leveraging the ability of obtaining a continuous location update of the users in the system. Since applications such as providing signal timing information to vehicles approaching or waiting at a signal, or the anticipated wait time for vehicles approaching a railroad intersection, or providing construction and maintenance alerts, all these help manage expectations of the users from the roadway system and reduces user frustration. So these are just a few of the potential applications that are being considered. So what is Georgia Tech's role in this project? Since we are taking a closer look at one of the applications to evaluate and quantify what the potential gains in safety and efficiency of operations could be. So we evaluate the reduction in delay in the emergency response. We quantify the improvement in mobility by measuring the total delay of all users of the system with and without the implementation of preemption, and the quantification of potential improvement in safety in terms of reduction in crashes can be roughly estimated by scanning for crashes involving fire trucks or other emergency vehicles. However, an empirical Bayesian study will have to wait until about 3 years past the implementation, since crash data needs to be compared across much longer periods of time. So we'll also look at implementation strategies that will maximize the benefits of the implementation. So how do we go about this? So unlike the North Avenue project, in this project, we do not have a technology already deployed on a test bed. However, we do have good data set to work with. We have the historical archive of the second by second signal phase and timing information at all the signals on the corridor and the crossroads. We have obtained data from the fire department for the location history of the fire trucks, but these consisted of updates once every 5 minutes. That resolution was not high enough to let us pinpoint the bottlenecks and figure out exactly where the delays are occurring. So we have come up with our own data collection plan. We are collecting data from these from about 15 to 20 fire trucks that operate out of these 6 fire stations in close proximity to the corridor. These fire stations were targeted because the fire trucks from these stations often have to travel along this corridor, or worse, have to cross this major arterial. So we are deploying equipment, essentially smartphones with a good GPS chip and some backup power, to collect second by second location data of the fire trucks round the clock for about 4 months. And this data gets automatically sent back to the Georgia Tech servers when the fire truck comes back to the station. We are currently working through the deployment of these devices. So once we have this data, we can perform a multifaceted data fusion, where we combine it with the traffic signal state information, the traffic count or demand information, and the travel time data on the roadways to extract and study the delay patterns for the emergency vehicles. We can also analyze the logs to figure out the emergency response request patterns, that is, which intersection do the vehicles typically travel through, and see if we can identify intersections that might work better for signal preemption if we route the vehicles through those intersections instead. We'll also look for cases where multiple fire trucks arrive at the same intersection together from different approaches, and see how do we handle preemption in such cases of conflict in an efficient manner. We can identify intersection approaches where the fire trucks are currently experiencing the maximum delay, the intersections that are likely to see high frequency of preemption requests, and such. So in addition to the benefits of making the preemption process seamless, the connected vehicle-based signal preemption also has the potential for other benefits. And since the location information for the emergency vehicles with connected vehicles is no more limited to the line of sight with a preemption request receiver equipment mounted on a signal arm, we have the opportunity to do multi-signal look-ahead preemption. So instead of providing the green after the arrival of the emergency vehicle at a signal, we can prepare the intersection by flushing out the vehicle queues in front of the emergency vehicles. By using a predictive approach, we can get the time to streamline the interruptions to the signal. Instead of introducing abrupt interruptions to the system, we ease the system into the chain, and thus thereby minimize the congestion impacts to the other users of the system. So in summary, we have looked at two of the connected vehicle projects today, which take two very different approaches. While both of them address the real-time operations, mobility, and safety, the North Avenue project takes a real-time simulation approach, while the Peachtree Industrial Boulevard, the Guin project, takes a more analytical approach here. So that's all I have for now.
Well, great. Thank you so much, Dr. Guin. We're now going to open this up for questions. So we're going to take a look in the chat area. Please use the chat area to ask any additional questions. We'd love to answer them this afternoon. And we have two that we received offline, so Professor Guin can go ahead and answer those while we're waiting for anyone else to submit questions.
Okay, so the question is, when can we expect to find connected vehicles technology in all cars? Okay, so that's one of the questions. Yeah, are we there yet? Now, well, so this has always been like a chicken and egg problem, right? Where do we have the OBUs in the vehicle to take advantage of the infrastructure, and on the other hand, do we have the infrastructure that will serve the vehicle or the data needs of the vehicles? And so we have tried to kind of jumpstart this with the Astro SPAT challenge and a lot of these smart city initiatives, where we have tried to encourage the states to go ahead and deploy the infrastructure. So at least one of the things is implemented, then the other can follow, so to take advantage of the information. So it's to further complicate things, as I was talking about, that's the 5G versus the DSRC race going on. And so vehicle manufacturers are always in a quandary as to figure out whether they should integrate 5G enabled equipments in their vehicles or DSRC enabled equipment. So and trying to stay agnostic means kind of delays the process, but we have seen some movement there when some way manufacturers are going with the 5G, some manufacturers are going with the DSRC. So to give a long answer to a short question, it's hard to tell. It's not going to be overnight, and so we probably need to see some legislation coming down from the center to kind of require the connected vehicles, the use of OBUs in the vehicles, some legislation to integrate connected vehicle technologies into the vehicles by the manufacturers or by aftermarket products or otherwise. So if I were to guess, it could be anywhere between 3 to 10 years. It's not going to be, again, it's not going to be overnight. It's going to ease into things. There's the fleet. As the fleet changes, you'll have more and more penetration of these. But the autonomous vehicle initiative, that has also given a good boost to the connected vehicle. So the autonomous and the connected vehicles, they kind of complement each other in terms of the information. So they work hand in hand. So one is kind of helping the other. So who knows? We might see things move faster than we expect. Okay, another question we have here is what measures are being taken to make traffic signal patterns more efficient or interconnected? So there's multiple things going on here. Georgia, for example, and so I'll talk about Georgia. Georgia is at the forefront of this initiative. And we have about 1,700 signals in the Metro Atlanta region that have direct connectivity to the center. These are on the regional traffic operations or the RTOP corridors. So these are connected in real time to the center. It sends its data back and back and forth. So you can send push the timing plans back to the signal from the center, as well as receive the state of what is the current operational state. And so we have direct connectivity to these signals. And there are, as part of the RTOP program, there are corridor managers whose duty, full-time job, so to say, is to manage the coordination and the efficient flow of vehicles on these corridors. So each corridor is managed individually with special attention on these, but we also have this remote connectivity to adjust things on the fly as necessary when there is an incident, when there is an unscheduled closure by an utility company. Those kind of things can be responded to on the fly. Also, with the advent of the connected vehicles, these things will be even more streamlined. Instead of having somebody noticing a breakdown of flow or the closure of a lane, since you know the position of the vehicles, and so if you'll see if there is a lane closure, you'll see all vehicles using one lane and slowing down. That can become a feedback loop into the system. So things can be changed on the fly based on the feedback directly from the system without having a human in the middle. Okay, moving on to the next question. See, do you see any smart corridor measures or technologies flowing over to similar key east-west surface street, such as the 10th, 14th, and 17th street? So yes, so we are in the early stages of deployment here. Yes, since I see the point when we are very Atlanta, we are very efficient in moving people vertically in the corridors. The horizontal corridors are not that efficient. Now, the first target of expansion will be the RTOP corridors, is what am given to understand. Means, I'm by no means speaking for for GDOT, but that's my understanding. But as we get more and more penetration of the roadside units, means we get better and better efficiency on all the on all roads. Means, I don't know if I answered your question sufficiently there. But yeah, means feel free to reach me offline and we can discuss this more. I'll move on to the next question. How would you advise an agency looking to use this type of technology to create an enhanced bus route that is a BRT without a dedicated right of way? So, one of the things that we were talking about is that, which is being considered under the Guin Connected Vehicle Technology Master Plan as the transit signal priority. So, so essentially, right now, the way I understand, we have the schedules for buses working as we look at the traffic movement patterns and we build in enough flexibility in the schedules, so that we can ensure that the vehicles arrive on time. However, with connected vehicle technologies, means we can be much more aggressive in real time in addressing any kind of delays in the vehicle, by giving priority to the buses, to the bus routes. Means we can be more aggressive in figuring out routes that we would not have otherwise considered, given the uncertainties associated with heavy congestion and delay on those routes. And so we can expand over to routes that we would have normally not looked at or avoided due to travel time reliability on those corridors. And there's several potential changes that are improvements that we have opportunities for improvement from leveraging the connected vehicle technologies here. Again, means I'm probably just barely scratching the surface here. The more closely we will look at it, the more penetration of the connected vehicles we have. And once we can go beyond talking from the vehicles to the infrastructure, or the infrastructure from once we go beyond V to I to V to V, where vehicles can talk to each other, and so we can streamline these more and more, and we can get greater efficiency and safety out of these systems.
Well, thank you so much, Professor. That's all the questions that we've received so far. So thank you, everyone, for tuning in today. We really hope you enjoyed this afternoon's webinar, our third in a 4-part series, the Georgia Smart Communities Challenge. Professor Guin, thank you so much.
Sure.
Thanks to everyone who participated and joined us for this afternoon's webinar. There's a 4th webinar coming up in April. We really hope you attend that as well. That'll be with Professor Omar Asensio, and he'll be speaking about the fourth community in our Smart Communities Challenge, the City of Albany, who's doing an open data portal and visualization of their housing data. So again, thank you to everyone for attending, and everyone have a great afternoon. That concludes our webinar.